Hey there. My name is Aaron Wilder. I'm a senior studying electrical engineering at the University of Iowa, and I want to take a few minutes of your time to give you a demonstration of my senior design project. For our project, my partners, Blake Riffle, Keith Rottinghouse, and I decided to create a working prototype of an mp3 player. We wanted a product that functioned in a similar way to a first-generation iPod. We wanted music to be stored on a removable micro SD card located in the side there, hardware volume buttons, a screen lock button, a lithium-ion battery that could be charged using a standard 9-volt plug, which is shown right there, a touchscreen user interface, the ability to organize songs alphabetically either by artist name or song title, and the ability to play a random song. But most importantly, we wanted something that would be challenging, something that we hadn't done before. So when we began this project, we really had no idea what we were getting ourselves into. We knew we would need a microcontroller and some kind of mp3 decoding chip, but we really didn't know what the software was going to look like or how the hardware was going to work. And since we wanted a challenge, we knew we weren't going to take the easy route and use any pre-made Arduino shields for playing mp3 files. Everything was going to be our design. So let me begin by just going through how the device works. I'm going to start by turning it off and then on again so you can see the startup step. When I turn the device on, the processor will first search through the SD card for mp3 files, find the artist and song names of these mp3 files, store them in separate arrays, and alphabetize them. Also during this step, which I'll show again, the screen also shows our project's logo, which my partner made. Our logo is a combination of our school's logo and Apple Corporation's logo. Our school mascot is Herky. He's a tiger hawk, and in that image, he's taking a bite out of an apple in a play on the Apple Corporation's logo. Kind of a combination of the two there. So after the setup, you see the main menu here. From here, you can touch the screen to select different options, find an artist or a song, and play it. When I select Display by Artist, each artist is displayed on screen. If there are more than 5 artists, then there are also scroll up and scroll down buttons located on the side of the screen, If the user selects an artist, then that user has his or her pick of which song to play by the artist. For example, let's pick me. We can see now that I have 2 songs, 440 Hz sine wave and 1000 Hz sine wave. It's a little blurry and light's kind of bad, I'm sorry about that. But let's say that I don't actually want to listen to either of those songs, because let's be honest, they're pretty bad. I can hit the back button to go back to the back one screen to go see the artists, or let's say I pick me again, I can hit the home button to go back to the main menu. If I hit display by song, I can see all the songs I have on the SD card. Let's pick one. How about, let's say Cocaine here. Cocaine by Eric Clapton. So now we see the now playing screen, which shows the song and artist name. From here, I can adjust the volume, make it go down. I can increase the volume, I can go back to the screen, or I can play the next or previous song in alphabetical order. I can also hit the pause button to pause the music. Upon doing this, the play button, the pause button turns into a play button, and if I hit it again, the play button turns into a pause button. And also, you can see it starts the song right back up right where you left off. So, going back to the main menu, I can play a random song. Doing this is pretty self-explanatory. However, a feature we added was that when you hit next, a new random song is played, as you would expect. But if you hit previous, the song just before this song in alphabetical order will be played. We did this simply because we thought that having 2 buttons that do the same thing was a little redundant, so we decided that the user should have some control over the randomness. Back to the main menu here again. I can also select output settings. From here I have the option to adjust the treble or bass, or I can also check the battery voltage. That looks like that, and if I hit the battery voltage, then I can see battery voltage at 3.71 volts. Go back to screen, adjust the treble, you can see that. And that's pretty much how this device works. So now let's take a look inside. This project had 6 parts. The ATmega 1280 is a microcontroller. The STA013 is used for mp3 decoding. The microSD card reader held the SD card, which contains all the mp3 files. The TFT LCD touchscreen is the user interface. A boost converter is used to step up the battery voltage to 5 volts for the display and microcontroller. And finally, a digital analog converter, or DAC, turned data that was output from the STA013 into an analog waveform. As I mentioned, the microcontroller we used is the ATmega 1280. It's an 8-bit, 16 MHz AVR microcontroller. It was programmed using the Arduino Interactive Development Environment, or IDE for short. We chose it because we had used Arduino before, so we knew how to use it. And we also really liked the I2C and SPI libraries that come with it. They really made the communication a lot easier. After soldering the chip to our PCB, we had to burn the Arduino bootloader onto the microcontroller. This is basically just a small program that runs on the microcontroller permanently that allows it to be programmed using the Arduino IDE. The external hardware buttons and the data request were connected to interrupts too. More on that next. The STA013 mp3 decoder chip was probably the most complicated and important part of the project. It acted as an I2C slave for control, such as adjusting bass and treble, volume, clock polarity, along with many other options. This chip acted as an SPI slave for mp3 data input. The I2C was 2-way, while the SPI was only 1-way. So the chip works like this. When it receives data over its SPI input, it stores it in a small internal input buffer. When it encounters valid mp3 data, it decodes it and sends it to the DAC. When the internal input buffer is nearly empty, it pulls a data request pin low and releases it when the buffer is nearly full. This data request pin, is connected to an interrupt on the microcontroller that is responsible for relaying more data to the decoder. Because we use a separate interrupt for handling data transmission, we can have gapless audio playback and use the screen at the same time. However, this chip does not just work when connected to power. Before being used, this chip needs to be configured. To do this, the microcontroller must first perform a series of over 2,000 I2C register writes to initialize the chip before it will function correctly. For this reason, we decided to store a file with all of the data that needs to be written on the SD card and do the configuration on startup. The next part of the hardware was the microSD card reader. It's a simple breakout board sold by Adafruit. Since SD cards are 3.3 volt, it has an onboard bidirectional 3.3 to 5 volt level shifter, as well as a 5 volt to 3.3 volt linear regulator. This was very convenient because it allowed us to power the STA013 decoder chip off of the same power supply. Arduino also had a seemingly awesome library for using SD cards, but it didn't really work. More on that later. The touchscreen that we used for the user interface is 240 by 320 pixels, 16-bit color, and is resistive as opposed to capacitive. This means you can still use it if you're wearing gloves, or you can use a stylus too. It used 20 pins, 8 of which were digital for parallel data transmission, and 4 were analog for touch sensing. We also connected the backlight to a solid-state relay, so the backlight can be switched on and off using the screen lock button. This allowed us to cut power consumption in half. The schematic for our power supply is shown here. We went with a LM3622 chip, which functioned as a lithium-ion battery charge controller. It senses the battery voltage and can either charge in constant current or constant voltage mode, depending on how depleted the battery is. Our battery was a regular cell phone battery, and the boost converter was a SparkFun board. We went with the SparkFun board because it offered an incredibly small package that would have been far too small for us to solder by hand. The DAC was the easiest part of the project. It was the only part that worked like it was supposed to the first time. As I mentioned, it takes data in from the STA013 using a 4-wire bus and converts it to a 24-bit analog waveform at up to 96 kHz with a dynamic range of up to 96 dB. The program we wrote for the Iowa pod has three main parts. First, a setup function which finds valid mp3 files and alphabetizes them, as well as initializes the decoder chip. Second, the main loop function checks for input on the touchscreen on each iteration. And third, the interrupts handle sending mp3 data to the decoder chip, as well as volume and screen lock control. As it turns out, the seemingly robust libraries for communication that initially attracted us to using the Arduino IDE as the base of our project caused a lot of frustration. The SD library that Arduino had for interacting with a file system on an SD card seemed at first to work really well, but upon looking at it further, we found that it seemed to use the SPI bus in a fashion that prevented the SPI library from functioning with anything else at all. This was still good for us because we needed the SPI bus not only for the SD card but for the decoder chip too. So after doing some sleuthing, we found a newer version of the library called SDFAT that had more capabilities, but we still encountered problems with the SPI bus. We then decided to use a separate bit-banking software SPI library for communication with the decoder chip. The software SPI library runs at 2 MHz, which is fast enough to allow us to play the highest bitrate of MP3 files at 320 kilobits per second. The user interface, which you saw during my demonstration, consists of both software buttons on a touchscreen and hardware buttons for volume and screen lock control. We also implemented a power switch on the top side of the device. Here's a picture of our Iowa pod with the lid removed. The enclosure was made with 3D printed ABS plastic measuring 4 inches wide by 5 inches long and 1 inch tall. Our custom PCB is mounted on standoffs in the enclosure with a battery below. You can see the decoder chip just above the screen, the SD card just below the volume buttons on the left over here, the power jack just below the screen lock button on the right, and the MOSFET level shifters between the decoder chip and the volume buttons. So this project had many challenges. Simply assembling everything was difficult in itself because everything had to be soldered by hand, and because we used a microcontroller with pins that had a 0.5 millimeter pitch, it had to be done under a microscope. It also took us a while to figure out that MOSFETs would work well for the level shifting. We initially used RC voltage dividers, but we weren't happy at all with the transient response or the wasted power. As I already explained, the SD library used the SPI bus exclusively, preventing it from being used by any other device. We also ran out of SRAM when creating arrays for storing the song and artist names. The 18MEGA 1280 has only 8 kilobytes of SRAM, compared to the first generation iPod's 64 megabytes, which, if you do the math, it turns out we had less than 0.2% of what the iPod had. So we could only store the names of 40 songs, the names of the song names and artist names of 40 songs. We also had to do many things for the first time in this project, which definitely added a lot of time and effort and frustration too. It was our first time using a CAD program to do 3D modeling. It was our first time designing a PCB. It was our first time using SD cards too, and our first time also using touchscreens. But by the time we finished our project, we could play the highest bitrate of MP3 files with audio quality indistinguishable from any other MP3 player currently on the market. We were able to look at the MP3 file's ID3 tags to find the song and artist names and alphabetize them. We met our size constraints with our enclosure. We were able to implement a power save mode that turned off the screen and ignored input and cut power consumption in half. And we were able to attain a flat frequency response from 20 Hz to 20 kHz. No human audible frequencies were attenuated at all. In conclusion, we were very happy with the way the project turned out. It was a very challenging project, and we learned a lot from it. Thanks for watching, and leave a comment if you have any questions. Bye-bye!